All right. So welcome everybody. So finally it's happening after quite some while, which I will now disclose. So Petalisp is a purely functional array language / library for Common Lisp. So it's designed as a language, but the integration with Common Lisp is so good nowadays that you wouldn't notice. And about the time I've been fighting C++, so the project started in May 17, 2016. I also presented in Mabea, and during this talk, at the end of the talk, I think you might see why it took so long to get everything right. And it's an opinionated project. I wanted to do something new, not boring. So one of the goals is extreme minimalism. Because I'm a researcher at heart and I want to learn about what programs can we parallelize, and I wanted to start from the simple cases and see whether that is possible and then proceed further. So this is the very simple case. And I also care about parallelism. So this language has no control flow whatsoever. From my compiler lectures, I learned that this is the hard part. So I just drop that and see how that I can get away with it. Also, there is no way to express even scalar programs. Yeah, that's you have to think a bit in parallel. And yeah, there are extreme opinions. For example, no syntax whatsoever. You have to construct your programs via Common Lisp calling functions. No side effects allowed, and I took no shortcuts in the implementation. So it's not like I didn't just optimize for one benchmark. I tried to get it right, you know. And most importantly, it's now finally ready for production, if you're brave enough. All right. So first part is the core language, because you have this approach where you can design something as a ball of mud like C++, where it accumulates features, and then the other way where you say, okay, we have 3 orthogonal things that produces the color space, or 5 orthogonal things, how we make concrete. Those are these images. And so very simple concept. The first one is being arrays. And for those that are not familiar to array programming, arrays are incredibly intuitive. You wouldn't even notice in the real world. That's why I put up these pictures. So one egg is an array of rank 0, because it's just 1. And then if you have a crate of eggs, you have rank 2. And no one would count, especially if you have a stack of eggs, you wouldn't just count them individually. You would count the height, the width, and the depth, and then you would just multiply. So you have kind of a product space. So arrays are actually super intuitive, and whenever people do parallel in practice, they will use arrays sooner or later. Below, you already saw some syntax below each graphic. And this is also the main theory slide. The rest of the slides, they all have fancy pictures. So shapes. In Common Lisp, an array is defined by a list of dimensions, among other things. And Petalisp generalizes on that. So in Common Lisp, you just say the axis 0 has that extent, and the axis 1 has that extent. So you can express the dimensions as a list of integers. Here you can have a step size other than 1, just because I wanted to avoid the discussion. And you can also have you have a starting other than 1 to avoid this discussion. And you can also have a step size. So your arrays can have gaps as long as they are regularly spaced. And 2 slides before I said I don't have any syntax. So now you might complain about the tilde, but I can calm you. So the tilde is just another function, and also a constant that evaluates itself. So this is the shape syntax. And yeah, you can have a shape of rank 0, and then you can have start and end, and you can have start, end, in the step size. And on the right, you see the indices. So every index in Petalisp is a list of integers. And a lazy array is just a function that maps from each element to a shape to some way to compute those elements. And there are 3 core operators of how you can operate on data. And the first and most important one, and probably known to most functional programmers, is lazy map. And the syntax for this is a function called lazy, whose first argument is a function, a Common Lisp function, and then any number of arrays that should match the number of arguments of said functions. So below, you see an actual Petalisp example. I define an array A, a regular Common Lisp array, an array B, and then happens the magic. So you take a lazy plus of A and B, and you call compute on that, because the result of this lazy plus will be a lazy array, which you can't peek inside, but once you call compute, what you get back is a regular Common Lisp array. So now you also know the way how the evaluation is driven and how you switch from lazy to eager again. So lazy is what happens by default, and for everything else you have to call compute. And something maybe went under the radar is you have a function lazy multiple value. So yes, lazy map supports multiple values. The only difference to common Lisp is you have to say in advance how many of the values you plan to receive, and the extra values that you don't get are initialized to nil in the usual way. So I didn't want to support parallel functions each returning a different number of multiple values, but I think that's fine. Okay, operator number 2 is lazy reshape. This is the only operator how you reorder data, and you can do so in any combination of these 6 elementary ways. So this is everything you can do with data is in the end boils down to these 6 operations. First one being you just pick some number. So you take a shape that is a subset of another shape, and those are the elements you process further. This is not invertible, of course, because you discard information. The second operation is broadcasting. You say I have one scalar and I turn it into 10, or you take a vector and you turn it in a matrix of some length. So broadcasting, this is the other operation that's not invertible. And then you have a lot of operations that you can invert. One being you permute the axis. So the order of axis doesn't really matter. You can just change that at will. And then you can move data. So just in this index space that's not necessarily starting from 0. You can scale with an integer constant or even a fraction, but the result has to be an integer. So you can scale your data. And the final one is you can drop an axis of size 1 because this is also an invertible operation. So this is everything you can do with data. And then maybe you're sweating because now there is a third complicated operator. But this one is extremely trivial. So fuse takes any number of lazy arrays and returns them into one array, into one lazy array. And the constraint being that the combination of all these lazy arrays has to be representable with the shape. But here I've shown both in pictures and in code how you can obtain that. So down below, we take the lazy reshape to broadcast both the integer 0, the integer 1, and the integer 2 to those shapes that correspond to the colors on the left, and then you fuse that, compute that, and then you get one array on the right. So those are the 3 operations, and that already concludes the first part, this is everything about Petalisp. You're now as knowledgeable as I am. And the question is, what can you do with these 3 operations? Is it just a theory thing where you can now talk about parallel computing, or is it actually useful? What are the limits? What algorithms can you write? What can you not write? I can already tell you that anything involving control flow or actually looking at the data won't work. Like searching a pivot element for Gaussian elimination wouldn't work because you would have to look at the data. But still, there are some domains where it works. The first one, and this one I had in mind all the time, was stencil codes, which is like filters where you blur an image by moving a kernel, some window over it and averaging things, or where you implement some game of life that most computer scientists should know. So those kinds of patterns you can really express because you turn each point of your mask into a separate lazy array, and then you just combine them with some function. Okay, so stencil codes definitely work. And what also works right out of the box is string processing and a lot of other kinds of processing, just because I support the same kinds of arrays as Common Lisp supports, and this includes arrays of type character and arrays of type T. So you can also lazy chair upcase some string, because a string is again just an array in Common Lisp, which is super nice. So whoever was involved in standardizing arrays in Common Lisp, this was quite nice. Right. And then I investigated further. Is there something else we can do? Another pretty nice thing is interpolation. You can just, because you can introduce those spacings in the arrays, and then you can shift them around and compute the middle between some points. So you can write an interpolation function. You can use that for image processing or even for fancy numerical methods like the multigrid method. So those things you can also do. And then it gets interesting. So I learned that you could implement reductions. In practice, it was the other way around. So I had a reduction operator, and then I learned I don't need it, and then I threw it out. So the main idea of how you write a reduction, I just wrote a single step here below. So if you take all the even numbered elements of an array and all the odd numbered elements of an array, bring them on top of each other. This is the code at the bottom. And then you sum them up. What you get is an array of half the length as before, which is the pairwise sums. And if you do that repeatedly, you get the sum of all the elements. You somehow have to handle the odd case too, but that's it. And suddenly you have reductions in a portable way using those operators. Once you have reductions, you can implement sums, the mean of something, statistics, and of course matrix multiplication, which is then just take 2D arrays, twist their index space, turn it into a 3D cube thing, and suddenly you have a matrix multiplication. And once you have matrix multiplication, you're basically you're golden. You can implement neural networks and profit from the hype. I wish I hadn't profited so much. Everyone was nagging me to write neural networks in Petalisp, but I didn't really have the time. So volunteers welcome to hack more on that. So CNN convolution in neural networks, that is just those stencil codes that I mentioned before, and everything else, fully connected layers, those are just matrix multiplications in the end. And then I thought, okay, this is pretty reasonable, makes sense to implement that language. And then I realized I can actually implement sorting using just map and reshape and fuse. And this works because I can map functions returning 2 values or multiple values. So I can have a pairwise sorting function that takes 2 elements and returns them pairwise ordered. And you can express what I show on the right graphically. You can implement batchers, odd even sort, using just those regularly spaced arrays. And suddenly you can sort arrays without looking at their contents in a lazy way. And suddenly you can compute the median, the smallest element, and all sorts of auxiliary things, which makes it tremendously more useful than before. And this is where I'm right now. But I have a suspicion that I can implement Fourier transformations, because if you look at this, this is all very regular, taking every second element and so forth. So this is definitely doable. And maybe you also have some ideas of the things I could still program. Okay, so much for the application side. And now comes a magic trick. And I will first prepare the stage of that magic trick, and it's not going to be exciting and confetti or anything, because we're programmers. So first have some C code. What I want to show you is the theoretical performance you can obtain on a modern machine like this laptop using standard practices like C code and the GNU C compiler or Clang. So this is a stencil code, a very simple one. Let me walk you through. So you have Jacobi's method, which is you take 2 arrays here with a pointer, and then you loop over all the interior elements of that. And what you do is you set the destination array center to the weighted average of the neighbors. So you're kind of blurring an image or whatever, or simulating a heat equation. And if you run that on a computer, on this computer to be precise, then if you use a single thread, one single threaded C program, what you get is 6 gigaflops, which is quite impressive. So this is more than the clock rate. So you see this uses SIMD instruction, so it does more than 1 operation per instruction. Pretty nice. And if you go to 6 threads, it's not a 6-fold increase because you're also memory bound, but still you're now at 15 gigaflops, which is so this is the straightforward OpenMP parallel C program. And if you annotate it the way I did it and said, okay, I know that the workload is homogeneous, there are no data dependencies, do a static schedule, you get 24 gigaflop of performance, which is pretty much the best you can do in terms of CPU on that machine. And now I'm going to show you a much more beautiful program. This is a Petalisp code for doing the same, but without any side effects and so forth. So the lazy at Jacobi method, the first line is a macro that makes sure that you can pass in both a common Lisp array and a lazy array. Then you just describe the interior. Then you take U and you shift it in all 4 directions. And what is after the shifting over the interior, you select, you add it up, and then you multiply it by 1/4 in whatever representation you have. So this is the program. And now I'm gonna run it on my machine. Can someone maybe hold them? Oh yeah, thanks. So I'm restarting the inferior Lisp, that I'm not cheating. Oh, wait. Good point. Yeah. Yeah. This is.
Still twitches.
Yeah. All right. So I'm loading Petalisp right now. Takes a while. Then I go to the right. I'm loading this benchmark code with this just the Jacobi function I showed before. I should also enter the package. And then I invoke this benchmark on a reasonably sized domain. And what I do is I do 100 steps, and that repeatedly for many seconds. And I compute the number of flops, which is.
The same processor?
This is this laptop, the very same hardware. And what you should see now, let me check the number because I can't see it. So this is 16 gigaflop, which is faster than the standard C++ thing. Not quite as fast as the best C++ program I could write, so I'm not happy, but it's maybe for comparison, if you write that in regular Common Lisp and you really care about it, what you get is 1 or 2 gigaflop to kind of, so this is the magic trick. And now think for a moment of how I turn this really declarative functional program with a higher order plus into code with that performance. No, it is. So how am I doing with time?
I thought you were.
Yeah. Okay.
You have 14 minutes. You could.
Wonderful.
10 minutes.
Okay, so I hope you're taking the time to think how I pulled off the trick.
Cool.
Yeah. Okay. So because really there was no cheating involved, compute is not a macro, it's truly a higher order plus and so on. So how did I obtain a performance that exceeds the C++ program thing? Andrea, you know it.
I have a theory.
Yeah.
I think in the C code, you should promise to the compiler that the destination does not alias source. Otherwise, the compiler cannot optimize it.
Okay, Andrea told me that I should have added a restrict keyword to the destination. But I think I did that and it didn't matter because the compiler, yeah, I'm pretty sure I tried that and didn't influence it. Anyway, so now I'm gonna walk you through why I still don't have a PhD and why this project took so long. Because I'm not a magician, I'm a computer scientist, so I am gonna explain the trick. So when you call compute, a lot of stuff goes on under the hood. And so the high-level program is transformed into an intermediate representation that is optimized, scheduled, run, whatsoever. A lot of magic happens, and so the individual steps. The first one is that when you have an array, it has pointers to its inputs, and in the end, what you end up is some kind of graph. And because you only have those three operators and Common Lisp array constants, you have a very simple structure. So the bright blue ones are the reshapes, and the green ones are the maps, and the dark ones are the fuse nodes. So really, really simple structure. And then these constructors for those lazy arrays are smart. For example, they compose consecutive reshapes into one and drop a lot of trivial instructions right away. And the second layer, and this was a surprise that was not so welcome, is that I realized you need to figure out the types of your resulting arrays also to make it efficient. So I wrote a portable type inference library for Common Lisp. And what it can do is you, for example, can say, okay, I have three variables, A, B, and C, for A being an integer, B being a double, and C being a short float, and I add them. And then please tell me what this Common Lisp plus is doing, and then it expands that into 2-arg double float plus of coerced to double float A, and 2-arg double float plus of double float from short float C, which is much closer to the machine, and you can almost see how that maps to the hardware. And also it derives that the value is double float. And this is how most of those arrays actually have a specialized element type. So I avoid the boxing and unboxing step. And typo is a separate project that you can also use, by the way. And then I turn this representation into an intermediate representation that consists only of something called buffers and something called kernels. And buffers correspond to stuff that eventually goes into main memory. And kernels, the green boxes, is a loop nest that has yet to be decided how to process, but it's basically a loop nest. And you see only one of them has more than 2 instructions. The 2 instruction ones are copy kernels that usually get optimized away. And one of them is the heavy lifting kernel that includes all the plus and product functions. And then this intermediate representation is optimized. The buffers are rotated so that the axes that have the best cache locality end up in the innermost loop and all that. And also reductions are optimized in a very interesting way to make them fast. And then you still have to partition it across parallel workers. So now you see that the graphs got quite a bit more complicated, and this is just a part of the graph. So every buffer is broken into parts that are small enough to fit into some ideally level 1 caches or something. That depends on the hardware, so you have to supply a cost function. But basically your large buffers are broken into pieces that can be easily put onto different cores or even machines or whatever. And this partitioning algorithm automatically introduces message passing, so I don't rely on shared memory at all. And it also minimizes the number of messages that have to be exchanged. So that was tricky to write. Another piece is that then you have pieces that have roughly the equal workload. This is the nice part, because otherwise scheduling is much harder. But in this case, I can break apart the work so that every work item has roughly the same cost. And then what I use is what's called a parallel depth first scheduler, where I first compute a depth first schedule, and then I walk that schedule and try to feed more than one worker, which I indicated with the colors, and then you end up with something that has not outrageous memory requirements and is still parallel. And also I augmented this scheduler because some array might turn into a lot of tiny pieces, and you want to process them in a way that you have temporal cache locality, which is super nice and super important. Otherwise you wouldn't get that performance. And then I generate Lisp code. This is kind of what I started out with, because Lisp code like this I never want to write again. This is the start of the project, and this is not even the part that does the work. This is the part that takes a kernel and an iteration space and sets up all the strides and the offsets. And then a final magic ingredient for the trick is, of course, you can't compile all the time, otherwise it would be super slow. So you have to do some kind of caching. And then the question is, what kind of key do you use for the caching, so that you usually skip the code generation and compilation of a kernel? The trick is you turn every kernel into a form that includes only what you absolutely need to generate fast code. And things like calls to expensive functions you would not inline. And like if you have contiguous access, that is important information. If it's not contiguous, you don't care necessarily about the step size and all sort of things. So you have a blueprint that encapsulates the essence of what's important, and you represent that not using regular const cells, but a library. I wrote a library called ucons for unique const cells in memory. And you represent it using unique conses, and then you can just do a EQ hash table to retrieve your code, and then you have fast code for whatever you want to do. And for example, the Jacobi that I showed generates 4 kernels in total. So you once have to compile those programs, and every future invocation is for free. And then finally, you have a worker pool. I was using a parallel, and then I wrote it myself. So you have the code that's driving it is loop for action vector and schedule. So you have a vector. So you have a schedule is a list of vectors that say for each worker what should I do, and each worker first copies neighboring points, synchronizes with the barrier, and then invokes some kernels. And that's it. That's the whole execution thing, and I'm on my last slide. And yeah, last slide summary. Petalisp is a language with only 3 core operators. What I didn't mention is it has implicit broadcasting all the time, everywhere by construction. So if you have a Jacobi function on rank 2 arrays, you can also invoke that on 100 rank 2 arrays and it would just work, or 100 by 100. And this really propagates throughout. So also the sorting function can sort any number of arrays of vectors of the same length at the same time. You have a 2D image processing function. You can apply it to videos or stacks of videos. So that's nice. You have lazy evaluation, so one headache less when writing libraries. The results are always reproducible. The code is portable Lisp. The performance is competitive. The next steps, I have a 160-page manual that I will publish in the next few weeks, hopefully, to obtain a PhD, finally. I also want Python bindings, because then the project would be open to a much larger community. And the obvious next step is hierarchical scheduling for me. So right now, it bugs me a lot that I only can show multi-core performance, because everything was written with message passing in mind. So it's really not hard to extend that to scale across multiple machines. Yeah, distributed computing. Also, I have a prototype for CUDA support, and maybe you have other suggestions. So that's it. Petalisp. Thank you.
Should we take some questions? Let's start with that. The time right there.
5 minutes.
5 minutes. Marco, maybe you could repeat the question.
Yeah.
Did you benchmark against Dialog?
Okay, so the question was, did I benchmark against Dialog APL? Not yet. So in order to have a fair comparison, I have joined with Andrew Sengul, whom we have heard earlier, and we are writing a April APL backend that uses Petalisp, and once that is complete, we can do a fair eye-to-eye, apple-to-apple comparison with Dialog APL.
You mentioned CUDA. Do you plan to like go for Vulkan or anything that's kind of more industry standard rather than on user?
Okay, so the question is, I talked about CUDA support. Would I also support things like Vulkan or other APIs? Yes, I would much rather target those. So I really, let's say I have to dual boot to 2 Linux distributions to develop CUDA on this machine. I hate CUDA, I hate NVIDIA. Maybe that answers the question. I'd love to have a replacement for CUDA that is more open. Thank you.
Thank you very much for the talk. That's interesting. How did you arrive at the 3 basic operations? Or how do you know that those are the only ones required? And are there alternatives that you have come across?
Okay, next question is, how did I arrive at those 3 operations? The answer is I distilled it down. So first I added new instructions until I could express those stencil codes and those examples that I had in mind. And then I realized that some operations like reductions I could actually implement in terms of the other, and they were not truly orthogonal, and then I dropped them. And in the end, I ended up with 3, which I think is reasonably small. There is another question by Charles, maybe.
And there's an RC question, is that
Yeah,
right?
there's a question from
And
John.
then we do an RC question.
So my question is, you said you can't reference elements, or you can't look at the elements in the matrix. You can only do these large, or these whole aggregate operations. So you can't do Gaussian elimination, which is pretty useful actually sometimes, I think. So do you know of anyway? This is relating to the primitives question now. Could you get most of the useful things? You can't even invert matrices like this. So do you have like some ideas for additional primitives you could add to tackling the big use case of actually inverting things, doing some linear algebra?
Okay, so the question is approximately that not being able to express Gaussian elimination seems a problem for linear algebra, and would I address that using more operators? And so that you would have to make a really strong case to get me to add something else to it. So it would have to be extremely beautiful. Otherwise, I wouldn't. And I think it's much better to try to work around, because this kind of forces you into a really nice way of thinking. And for example, a Gaussian elimination is just not a parallel algorithm. a proper one. And instead, if your matrix has a certain structure, you could implement something like a conjugate gradients method and still solve your system of equation for many cases without looking at the data. So the approach right now is not to do everything for the programmer that they say they want, which a lot of other languages do, but just say this is the way you can do it, and then we guarantee you good performance. Okay, the question from ISC.
In a similar vein, what do you make of sparse arrays or representations that aren't represented as a flat sequence of values? I heard in a lecture they're useful for evaluating deep neural networks.
Okay, so about sparse arrays, I plan to support that in the beginning, but then after some pondering about it, the problem with sparse arrays is so a dense array is clearly defined. You know everything computationally, the number of loads. Whereas a sparse array, there are zoos of sparse arrays with different kind of structures, and no library deals with all of them well. So it's always some kind of special casing, and I decided to not support that, and if you want to have something like sparse arrays, you can always have a dense array that stores all your columns or all your rows, and then you just put in lists of something in there. So there will be no sparse array support in the near future. Thank you.
Have you thought about using Petalisp for doing high-level synthesis on, say, like an FPGA?
So if I understood the question correctly, the question is using FPGAs as a backend?
Yeah, sure.
Yes, yes, I have thought about this. I was approached by several people working on FPGAs. There is in principle nothing against generating some FPGA style code. Yeah, that should just work for some programs. Of course, only a subset of Common Lisp would work on an FPGA. But yeah.
All right, I think that's good, right? We're pretty close to the time. All right, thanks, Marco.